All right, so we should be good to go. I'm just going to do a couple of things. So hopefully you have just said hi in the sector forum. We're going to start the lesson very soon, and we're going to get straight into it because I do have a lot to cover today. And chapter 5 or 5.1 has got a lot of things in it, so we're just going to get straight into it. So if you want to guess where I am in the sector forum, you can as well. So every day I'm going to have a different background behind me, and we'll see how we go. Also, the other benefit of YouTube is that after the video has finished, so after I've finished streaming, the video will be posted online and you guys can watch it at a later time as well. And you can obviously pause the video and even watch it at twice the speed and so forth. So we've got 8 viewers at the moment. We're just going to get the OneNote thing ready. And we're about to start. Thank you for your patience today. I know it's a little bit weird, but yeah, we'll get straight into it. So hopefully people have found the channel. So Cherith said hi in the forum. So yeah, if you want to subscribe to my channel as well, and then click on the notifications bell, you'll get notified every single time that I stream live. And so it might make it easier to actually just click on a link to get to my channel rather than having to search my channel every time. All right, let's get straight into it. We've got an hour to try and get through everything. After the live stream, we will go back to Teams, and if anyone's got any questions regarding the lesson today, I'd recommend that you just write those questions down somewhere so you can remember them, and then when we go back to Teams, you will be able to ask those questions. All right, let's get into it. All right, so hopefully you guys can see that okay. So we've got the notes up on the screen. So exercise 5.1 covers domain and range of functions. So some of this stuff, if you have done extension maths back in year 10, you would know a little bit about this, but I'm going to cover this as if you have no idea or if you've forgotten it completely. So there's lots to cover today. So the first question I pose is, what is a function? What is a function? So what I've got is a scenario here involving soccer. So I know not everyone likes soccer, but I'm going to use it as a bit of an analogy to describe what a function is. All right, so say we've got 5 players, okay? So these players over here, and they take part in a penalty shootout. And it's not just a normal penalty shootout, it's a special penalty shootout. It's the one where we've got each of these 5 players, they take 8 shots each, and then they record how many goals they've got out of 8, okay? So I've got a little diagram here, and the diagram shows the 5 players that are taking part in this competition. So we've got Alex, Bob, Chris, Dan, and Eric. In this circle here in this set, we have all the possible scores that they could get out of 8. All right, so I've got 0, 1, 2, 3, 4, 5, 6, 7, or 8. 8 meaning if they scored 8 out of 8, they scored every single time. The arrows here represent their scores. So Alex had the 8 shots on goal, and his arrows pointing to the number 5. So that means Alex got 5 goals. Bob scored 3 goals, Chris scored 5, Dan scored 7, and Eric scored 6. Okay, so from this little example, it's quite clear, I hope, to see that a single player, their arrow can't go to 2 different numbers. Okay, so what that means is, say Alex took his 8 shots, he can't score 2 different totals out of the 8. It's impossible. All right. So each element, each thing in this first circle, in this first set, maps to a single element in this one over here. So each element in the first set maps to only one element in the second set. And this is an example of a function, okay? So anytime you have this kind of scenario, not necessarily all to do with soccer, but anytime you have, say, your input values or your starting values mapping to a single element in the second set, that would be called a function, okay? So the first set, this thing in this part of the diagram, we call this the domain, okay? So the players in this particular example are called the domain. They're our input values. The second set over here, this is called the codomain. And for those of you doing extension maths last year, you might not have heard of codomain before. It might be pretty new to you. But codomain is essentially all the possible numbers that these players could have got. Okay, so they could have got any scores between 0 and 8. So that's called the codomain. Finally, the numbers that the arrows point to form the range. Okay, so the range are these numbers here, the 3, the 5, the 6, and the 7. So they are all the possible scores that the soccer players got. So just summarizing what we're talking about there, in this particular example, the domain, and I'm using these curly brackets to indicate the set, okay? So the domain are all our players, so everything in the first set. So Alex, Bob, Chris, Dan, and Eric, that's the domain. The codomain is all the possible scores that they could have got. So 0, 1, 2, 3, 4, 5, 6, 7, or 8. And then the range finally is actually the output numbers, what the actual scores that people got, okay? So 3, 5, 6, and 7. I haven't included 5 twice in the range. That's because we don't need to say the numbers if they've happened twice. So I've just, every single time a number has got an arrow pointing towards it, I've just listed it here. That's called the range. That's your output values. That's your answers, I guess. There's different types of functions. Okay, so we're going to talk about a few of these different types of functions. So notice I'll just zoom out even further. Hopefully it's not too small on your screens. Notice both Alex and Chris scored 5 goals, okay? So this means that these two arrows here are pointing to the same number, okay? So these two arrows in the domain are pointing to the same number in the codomain. What this is called, this type of function is called a many-to-one function, okay? So that means when there's more than one element from the initial set, so the domain, when there's more than one element from the domain maps to the same element in the codomain or the range, it's called many-to-one, okay? So many-to-one is this kind of scenario that we've got. If we had a scenario where each element of the domain maps to a different element in the range or the codomain, then the function is called a one-to-one function. Okay, so I've got a couple of examples here. So here we've got like what we had with the soccer example. We've got the two sets, the domain in this thing and the codomain over here. The range, of course, would be D and F. Okay, notice we've got two arrows pointing to the same value. So this is called many-to-one, just like our soccer example. This second one is an example where we have one-to-one. So what that means is every single domain value points to a different thing in the second set. Okay, so all the arrows point to a different thing in the second set. We still have an item over here that an arrow doesn't point to. That's still okay. That's called a one-to-one function. And over here is an example of something that's not a function. Okay, what we've got here is a situation where we've got an element in the first set, this Q, and its arrows are pointing to two different things at the same time. That's called one-to-many, and this is an example of something that's not a function. And we'll talk a little bit more about those type of things in a second. So that's all kind of like general terms, but what's this got to do with functions like f of x equals x squared and that type of thing? What's that got to do with that type of thing, okay? So what I've got underneath, I'm going to have some examples and some functions to do with these type of equations. And what I want you to do is I want you to have a go at thinking about which of these functions are many-to-one or one-to-one, okay? So if you wanted to pause the video right now, I've got this first set here, the second set, and the third example here. So in this first example, we've got the function square root x, and we've got the domain of these values over here, and they're mapping to these range values over this side. So we're going to label this as either one-to-one or many-to-one. And if you want to pause the video right now, you can do that, and you can maybe just in your head think about which of these is the right ones. Okay, so we're going to continue. So this is the results of this first kind of mini example. So the first example here is definitely a one-to-one. You can see these arrows going just to one number each time. And so this is an example of a one-to-one function. This example here, the function's x squared. We have -3, it maps to 9, and we have +3. It also maps to 9. So these two numbers mapping to the same number over here. It's a bit like our soccer example. So this is called many to one. We have many arrows pointing to one number in the range. Okay. And this one over here is also a one-to-one function. Each of the numbers in the domain, each of the numbers in this first set are mapping to just a single number in the second set. Okay, so hopefully you got those right. And then what I've also got underneath is just to show you what the graphs of each of these look like, because we're going to refer to these graphs a lot of the time as well, because when you graph these functions, you don't normally write them in circles with numbers in them, right? When you graph them like what we've got here, these type of graphs. So this one here is called a one-to-one function. This one here is a many-to-one function, and this one here is a one-to-one function. These are just the corresponding graphs to these rules up the top here. The reason why this is many-to-one is because we could have an x value of -3 and another x value on this side as being 3, and they map to the same y value. They've got the same y value, okay? So for example, if I was to draw a horizontal line through this graph, it's going through 2 points all the time, okay, except for down here obviously, but in this section here it's going through 2 points, and that's another clue that it's a many-to-one type of function. The next thing I want to talk about is what is this vertical line test. So a vertical line test is when you draw a vertical line somewhere where you see the particular function. So where you've got the domain of the function, so somewhere where you see the graph, if you draw in a vertical line and it only cuts the graph at one spot, so not more than one spot, if it just cuts the graph in one spot, that means that that type of graph or that type of thing is actually a function, okay? So it's kind of like a test to determine if something is a function or not. So what I mean is I've got some examples underneath here. So I've got, this is just a linear graph, and I've tried to draw in a vertical line in red, and as you can see, the vertical line has just cut the graph in one spot. So this passes the vertical line test. So this means this is a function. Cool. This one is a circular graph. It looks more like an ellipse or an oval. If I draw in a vertical line through this, you can see that it cuts it in 2 spots. It intersects in 2 spots. This fails the vertical line test. The vertical line test says if it cuts through in just one spot at any part of the graph, then it is a function. If it cuts through more than one spot, it's not a function. This next one is a parabola. And as you can see, if I draw my vertical line anywhere that I've got the graph visible, it's only ever going to cross the graph in only one spot each time. So that's a function that passes the vertical line test. And then finally in this one here, we have a situation where we have a really weird graph. It's kind of like a cubic on its side. But again, if we try and draw a vertical line anywhere in my graph and it cuts it in more than one spot, then it fails the vertical line test. So you might argue, okay, Mr. Wager, I can draw in a vertical line just over here and it just cuts the graph in one spot. Therefore, it would pass the vertical line test. But no, anywhere on the graph, if you move the vertical line from left to right and it cuts through the graph in more than one spot, it fails the vertical line test. Therefore, it's not a function. Says here we could also use a similar horizontal line test to determine whether a function is a one-to-one function or not. So if it cuts through the graph in more than one spot horizontally, it means it's not a one-to-one function. Okay, so we've covered a lot about functions. The next question I pose is, what's something that's not a function called? So what about these things? What are they actually called? What's the name for those things? So the second and fourth graph, these ones here, they are called a relation. A relation. So relations are anything that aren't functions. And I've got a little bit of Venn diagram to explain the difference and the similarities between relations and functions. So functions are specific type of relations. Relations cover everything, okay? So relations are any type of graph. Any type of thing we can consider a relation, okay? So relations are kind of like the governing body. Everything that you can think of in terms of graphs is considered a relation. But within the relations, there is a specific type called functions. And they are what we've just talked about, these type of things. That's a function there, that's a function there. But these two things here, these two graphs, they don't fit in the function mold, so therefore they would fit in this region on the outside. They are a relation, but not a function. So not every relation is a function, but every function is a type of relation, if that makes sense. So I've got an example here. So I've got x squared plus y squared equals 16. If you can remember circles from last year or the year before, that's a circle equation. This is a relation, it's not a function, okay? This one, x plus y equals 4, if I was to plot that, that would form a linear line, a straight line, and that is a function, and it's also a relation. The last thing I want to talk about for this type of stuff with functions, and before we go through a couple of examples, is this whole idea of the machine analogy. All right, so this is just another way to think about this kind of stuff. So imagine you've got a machine, all right, and it's a special type of machine where if you feed it numbers, called input numbers, so if you put a 1 into this machine, what it will do is it will do a calculation, and then at the end it will spit out a number, okay? It'll put a number, it'll give an answer, okay? So if I put 1 into this machine, and this machine says it's going to square the number and then add 3 to it. It's called the square it and add 3 function machine, all right? So if I substitute this 1, if I put this 1 and feed it into this machine, it's going to do the calculation, it's going to square it, and then add 3 to it, and then out spits the number 4. The result is 4, the answer is 4. If I feed it the number 2 into this machine and say, okay, square the number 2 and add 3 to it, out would spit the number 7, okay? The result, the answer to that calculation is 7. And similarly with the numbers 3, 4, and 5, if I feed those numbers into the machine, the results of those calculations will be 12, 19, and 28. What's that got to do with anything? Well, what I want you to think about is back before when we talked about the 2 sets of examples for the soccer example, and we talked about different types of functions, we talked about the idea of domain and range. What I want you to do is, in this particular example, I want you to tell me what the equation of this function machine is first. And then what I want you to do is think about what the domain of this machine is and what the range of this machine is, okay? So what's the domain for this example and what's the range for this example? Again, if you want to pause the video and try this for yourself, I really encourage you to participate this way and not just do nothing during this time. To this, the function in this example, the square it and add 3 is x squared plus 3. That's what the function is. That's the equation of the function. The domain is all these input numbers. These are all the numbers that we put into the machine. So 1, 2, 3, 4, 5. That's kind of like the x values, if you like. We'll talk about x values in a second, but these are like our x values. They are input numbers. They are the starting things. We put those numbers in, we do a calculation, and out comes the results. The range are these answer values, the output values. So 4, 7, 12, 19, and 28. They're the y values. They are the output numbers, okay? So they are what we consider the range. So every single one of these, I'll draw in those green arrows, a bit like the soccer analogy. Each of these maps to the range, okay? So the domain maps to the range. Next thing I want to talk about is natural domain and range of functions. So we kind of introduced the idea of domain, kind of introduced the idea of range, but now let's talk about it in terms of graphs. So if we're not given a specific domain, the natural domain is all the possible x values that the function can handle. So think about a machine, think about all the possible x values, think about all the possible numbers that can go into the machine that the function can handle. What I mean can handle is some equations and some functions, when you substitute in an x number, when you try and input an x number, it fails or it gives an undefined value, okay? And we'll talk about a couple of examples in a second about that. So here is 3 graphs, 3 equations that we're going to look at. So the first one is this one. F of x equals 1 over x minus 3. It's this graph over here. So the question says, what is the natural domain of this? So we're going to think to ourselves, what are all the possible x values that this function can handle? Okay. Also, we need to specifically mention in our domain instructions any values that will cause the function to be undefined or the function can't handle. Okay, so in this first example, you got to think of, all right, what are the possible x values that this thing can handle? But also, what are the possible x values that it cannot handle? Okay, it's got something to do with this asymptote right there. Also, the second example, I've got a linear graph. What is the domain of that one? And I've got a square root function over here, h of x equals the square root of x minus 3. Again, what I'd like for you to do is pause the video and try and think about what the natural domain is each of these functions. And in a moment, we'll tell you what they are. Okay, so the first one, let's just start with this one. So I've written down here, it's kind of special fancy speak, but this is how you kind of write the domain and range things in this chapter, okay? So we start off with these curly brackets. It's a formal way of writing the domain. We say, x belongs to the set of all real numbers, okay? So in this example here, x can be any number, any real number you like. And the real numbers is got to do with any numbers that you know of. There's other types of numbers called complex numbers, which are to do with square root of negative values. But in the purpose of methods, Year 11 methods, we're only really going to be speaking about real numbers. So that we just talk about x as being an element of all real numbers, means x can be anything, such that, that's what the two dots mean there, such that x cannot equal 3. That's our restriction. That's our condition in here. In this particular example, 3 for x is the only thing that this function cannot handle. And we put our little restriction afterwards. So we say x can be any number except 3. That's what that means, okay? So that's the first domain problem. The second one, this linear one over here, well, if you think about it, there is actually no value of x that this function can't handle. I can put in -5 into it. I know it's not visible on my graph here, but if this graph continued on forever in that direction and that direction, I could substitute x equals -5. I could put x equals -3 billion, and it would still be able to work out what a result is. We'll work out a corresponding range value. So that when we do that, this is the default scenario. So the domain for this example is x can be any real number. That's how we write it. We use the curly brackets to represent domain and range. X can be equal to any real number. X belongs to any real number. Finally, the square root one. X can belong to any real number, except the condition for this one is x must be greater than or equal to 3 for it to work, okay? So notice this first one, we said x can't equal 3 because of this restriction here. If it was equal to 3, that would cause the function to be undefined. In this one, if we substitute an x value that was less than 3, so maybe 2 or 1 or -2.5 or something like that, what's going to happen is when we do the square root of that function, it's no longer going to give us a real value. It's going to give us a complex number. So therefore, it's not part of our domain. It's not something that we can include in our domain. So think about it in terms of my graph, okay? So the graph starts at 3 and goes onwards. So this domain is telling us what are the possible x values that are in our graph. So it goes from 3 and higher. X is greater than or equal to 3. You could potentially say the domain as being x is an element of real numbers, but x does not equal values that are less than 3. But rather than saying x cannot equal values that are less than 3 or less than or equal to 3, actually it can equal 3 for this one. But rather than saying it can't equal this inequality, we just say what the x values can handle in this particular function. It's easier to do what it can handle for inequalities than it is for this one. Just put a line through it for not equaling 3. Okay, what about the range? So the range is all the possible y values. That's probably the easiest way to think about the range. The range is all the output numbers, all the answers, but it's all the possible y values that the function produces from the domain, okay? So let's have a look at the same three graphs we've got here, the same three functions. What I'd like for you to do again is pause the video and see if you can tell me what the range is for each of these graphs. So think about it in your head, okay? So pause the video, think about what the range is for each of these functions, and then we'll go through the answers. Okay, so the range for the first one. So this one here, remember range is dealing with y values. Again, we're using these curly brackets, which is a little bit unusual. I know, it's just a bit weird. What we're going to do is we're going to think about all the possible y values that this function can result in. Okay, what are the possible y values that it generates? So notice we have this horizontal asymptote at y equals 0. That's the only case in this particular graph that this function can't get a result of. We can get all these other y values, but we can't get a y value of equal to 0. So the way we write that is that y can be any number except 0. That's the restriction. This function here, the linear one, y can be any graph in here. There's no restriction whatsoever. So we write that by saying the range for this one is y belongs to all real numbers. And then this final one, we can say that the range, if you look at the graph, see how none of the graph is below the x-axis, but at y equals 0, we do get a result. So we say for this one, the range for the y values is, it can be any number, but the y values must be greater than or equal to 0. See how the graph is above the y-axis? So y has to be greater than or equal to 0. That's the range. That's kind of all the output values here is going to be that. Okay, I'm just going to do something. There we go. Okay, we're back online again. Cool. All right. So that's kind of the end of exercise 5.1, the notes for it. But today's a bit weird because I do need to talk to you guys about exercise 5.2 as well. So for exercise 5.1, I've written here, you're going to need to know about how to graph certain functions using your understanding of transformations. This idea of domain and range builds upon your understanding of transformations. So if you don't know how to graph basic parabolas or cubic graphs or square root functions or exponential graphs, you'll need to go back and hone your skills with those type of things. What I'd recommend that you do is maybe use Desmos to try and reinforce your learning there, to try and help you with the graphing aspect of what these graphs look like. You could, of course, use your graphics calculators as well. But here are the questions that I'd like for you to do of exercise 5.1. These are visible in the OneNote notes. So when we go to exercise 5.2, you can come back to these and see what they are. Okay, so we're going to take just a short break of 1 minute while I get things ready for exercise 5.2. So just bear with me. When I mean short break, it's literally a very short break. All right, so we're back into here. As I said, after this session, hopefully it won't go for much longer than 10 more minutes. What we'll do is we'll go back to Microsoft Teams and we can do like a question and answer session. So hopefully you've been writing down some questions along the way as we talk about the notes and things in OneNote. All right, so let's do this. Exercise 5.2 is got to do with circles and relations, okay? So what we mean in this exercise is we're going to talk a bit about circles and then we're going to talk a bit more about relations. I did introduce relations just a few minutes ago, but we'll kind of elaborate a bit further on it. So just look at a quick revision about circles. I know we covered circles way back in year 9, maybe year 8, I can't remember, but circles are not functions. They are relations like we talked about very recently, 20 minutes ago. Here is the default circle equation. Actually, the real default circle equation is like x squared plus y squared equals r squared. But this is kind of like the main one you see. So in brackets you have x minus a all squared plus y minus b all squared equals r squared. Different textbooks use different letters for the a and the b. But the main thing to note is where you find the center of the circle is located where the a and b are, and it's always opposite to, I guess, the sign, or imagine solving the bracket part equal to 0. That's kind of like what the x and y values of the center of the circle is. So if it says x minus 3, the x value of the center of the circle will be positive 3, kind of like the opposite there to the minus. The radius, of course, is when you take the square root of this number over here. So the radius is not just this number over here, we need to take the square root of it. So the radius is just going to be r. Okay, so hopefully that reminds you a little bit. So I'm going to have a quick example here, if you can remember how to do circles. And again, I'm going to get you to pause the video and you can work out the answers to these problems here. So I've got these two circle equations. One is nice and easy to spot the center, and the other one you need to do a little bit of work. So I want you to see if you can remember how to work out the center and radius of these two examples. Again, if you want to pause the video, in a moment I'll show you how to do it. Okay, so in this one here, the center is, you just look at the clues in the brackets, you can see that the center is going to be at -3 and 4. -3, +4. And when you take the square root of 16, you get, whoa, that's a bit weird. Sorry about that. When you take the square root of 16, you get 4, and that's the radius of that circle. So this center is at -3, 4, and it has a radius of 4, okay? The second example, we need to do a little bit of work. So if you can remember back in year 9, when we would have seen this for the first time, maybe even year 8, you have to kind of put the x and y values together, so the x terms together and the y terms together. And then if you can remember back to there, you have to complete the square of this section here and complete the square for the y values. So complete the square of the x terms, complete the square for the y terms, and any constant numbers we then collect like terms and put them on the right hand side to manipulate the 6 over here. Okay, so this is what it looks like. So this first section, the x's, when I complete the square, it's x minus 1 all squared minus 1, because that's what we have to do to complete the square for that. When I complete the square for this, it's y plus 3, so half that term is 3. And then we minus 9, because that's what this number here squared is, minus 9. And then the two constant terms, we want to simplify those. So the -1 and the -9, let's put them on the other side, or let's add 1 and add 9 to both sides if you like. And we end up getting 16 as the result over on the right hand side when I add those numbers together. And on the left hand side, we have a clear picture now of what the center of the circle is going to be. The center is going to be located at +1 for the x value, -3 for the y value, and the radius is of course the square root of 16, which is 4. Okay, hopefully that brings back good memories. All right, what about other types of relations? So circles are a type of relations. What about something like this? So I've got this equation here. I've got y squared equals x. What I want you to think about is, what does that graph look like? And what is the domain and range of y squared equals 6? Okay, so what does that graph look like? And what is the domain and range of that thing? So what I'm going to go straight into this. So this is what the graph looks like. Y squared equals x. And what it really is, it's a graph that's actually made up of two components, two functions, if you like. So the way we get to that is, imagine we've got our y squared equals x, that's our starting point. And then we take the square root of both sides. So if I take the square root of the left-hand side, it's just going to be y. But when I take the square root of the right-hand side, we have plus or minus the square root of x, a bit like solving those quadratic equations, right? What do each of these graphs look like? Well, y equals the square root of positive x looks like this, graph like that, and that's a function, right? So if I was to draw a vertical line through any part of this graph, it only cuts the graph in one spot, so that's the most it does, so therefore it's a function. The graph of y equals negative square root x is this one underneath. It's this one. It's kind of like a reflection over the x-axis, as you would expect from transformations. So this is the graph of y equals negative square root x. It also is a function. Combining those two together gives us our original graph, y squared equals x. So it looks kind of like a parabola on its side. And this one, where the two graphs combined, or this y squared equals x, is not a function anymore. It's a relation, because if I draw a vertical line anywhere in this section, it's going to cut through in more than one spot. What's the domain? Well, the domain of our graph here, so we're just going to really focus in on this function here, not function, this graph, this relation. The domain here is x can only be greater than or equal to 0. You can see on my graph here, I've got no negative x values that the graph can handle. X has to be greater than or equal to 0, okay? The range is, there's no limitation for the y values. Like the y values go on and on forever, infinitely upwards, and they go infinitely downwards in the negative direction as well. So if we were to zoom out on this particular relation graph, it will go forever upwards and forever downwards. So the range for this function, this relation, is y belongs to any real number, can be any real value. Got one more example, and it's this one. What are the equations of each parabola? So I've got these two parabolas. So parabolas on its side are still called parabolas as well, and I've got this blue one here. All we know is that they intersect at the origin, and they also intersect at this coordinate here, 4, 4. All right, so we want to know what the equations of each of these parabolas are. So let's look at what we've got. The blue graph is our stock standard quadratic, okay? And a stock standard quadratic, it's not moved left or right, it's not moved up or down. It could have a vertical dilation scale factor, so I've written it here, y equals ax squared. It could have some form of vertical stretching, but we don't know what that is at this stage. This red graph looks a lot like the one we just had up here, this parabola on its side. The default equation for that is this thing, y squared equals x. But we could have some form of dilation factor here, so we'll call this y squared equals bx. Both graphs share the coordinate 4, 4. And what I'd like for you to do is, using this coordinate, substitute this coordinate into both equations and see if you can solve for a and b. Pause the video now and see if you can try this for yourself. Okay, so for this one here, all we need to do is substitute the known coordinate. Don't do 0, 0, because that's not going to be very helpful for you. Use this one here, the 4, 4 coordinate. So the blue graph, the y value is 4 at this coordinate, and the x value is 4. So substituting that in, I've got 4 equals a times x squared. So 4 equals a times 4 squared, which is 16. If I solve that equation, I get a is equal to a quarter, or a as being 0.25. And that is the equation of my blue graph. Nice and easy. The red graph, same thing. Substitute the y value and the x value from the known coordinate, from 4, 4, into your rule, into here. So we get 4 squared equals b times 4. 16 equals 4b. So therefore, solving that, you get b equals to 4, which is 16 divided by 4. And so the equation for this one is y squared equals 4x. And they are the two equations of those two parabolas. Final thing I want to mention is your work, the questions that I'd like for you to do for exercise 5.2. They're listed here. And as I mentioned, we're going to jump back over to Teams now. So Microsoft Teams, I'll start up a new meeting, and we will be happy to answer any of the questions that you have about today's lesson. Okay, I look forward to